Hi students, welcome to this video where we'll be going through some of the earlier exercises on chapter 14, interactions through the work application of forces. So please have your theory book ready and we'll go through from page 61 to 66. Right. As this part of the workbook is pretty straightforward, so there will be certain components that I will just need you to do a quick self-check, and if it's correct, just give yourself a small tick. Right. If it's wrong, just put in the corrections. I think most of the questions here are quite straightforward. So let's talk about the first question. Now this first question, you're supposed to describe the force that's being exerted using the different words push, pull, twist, as well as squeeze. Alright, so in this case, it shouldn't be that much of an issue. I just wanted to use this chance to talk about some of the forces that you have learned in this chapter, and they are actually what I call the non-contact forces. Right, so I hope you still remember that non-contact forces are forces that are not in contact with the substance, right? So two of the examples in our syllabus are magnetic forces as well as gravitational forces. Right? So I thought this was a good chance to show you about the application of these two forces. The other four that you see over here, they are all called contact forces. Now, not all of them are what we learn in our syllabus. Some of them are what we call applied forces. Some of them are what we call tension. So if you're interested, you can go and Google about them. But in our syllabus, we are only interested in magnetic force, gravity, as well as friction, which I'll talk about it later on. Let's move on to the second page. Now this second page is quite straightforward. We're just supposed to link the effects of forces, right? So forces can have various effects on objects. So you can either start an object, stop an object, change the shape, or change the direction of movement. So in these four examples here, you're just supposed to categorize them based on the keywords that's being provided. Right? Maybe at this point, I just want to point out, if any point in time where you feel that your answers tend to contradict what is being presented over here, and you would like to clarify, please go into Google Classroom and key in under the private comment, whereby you can let me know if you have any questions. If not, I'll move on to page 63. Now in page 63, the first question, question 3, who is right? So in this question, there's a context of Sarah and Lisa being at a supermarket, whereby they're pushing a trolley. So there were some statements made by each of them. Okay. In the first part of the question, part A, we're supposed to think about what are some of the effects of force that is being shown in this question. Right. So of course, one of the most obvious effects is that force is needed to start an object to move. Secondly, it's also that force can be there to slow down an object. Right. So in this example, there's actually a pushing force that's moving the trolley forward, but there's also a friction force that's slowing it down. So that's why when Sarah stops pushing, the trolley will eventually stop moving because friction will be there opposing the action of the trolley. So of course, you can also state that one of the effects of force is that it can change the direction of the object. So as she's pushing around, right, as she navigates throughout the supermarket, the trolley will move in different direction. So what's the force that causes the trolley to slow down and stop? It is friction. This one is quite straightforward. Now in terms of who is correct, so let's take a look at their statement again. Now, the interesting thing is that both of them are actually correct. So let's take a look at the statement individually. For Lisa, we mentioned that to keep an object moving, a force is always needed. Now, this is quite intuitive, right? We know that if you want to make sure that the object doesn't slow down, right? You don't want the friction to overcome the force. You need to continuously push the trolley. So to ensure that the trolley can continue to move, Lisa needs to continuously push the trolley in order to overcome friction. Hence, Lisa's statements actually, it makes sense because if you think about it, if not, the trolley will be slowed down by the friction that's at work. But if you take a look at Sarah's statement, right, it's actually conceptually correct as well. It's actually possible for an object to move without a force. Now, why is that the case? Imagine you have an environment whereby there is no friction. Right? So imagine that, let's say that there's this supermarket whereby Sarah is pushing the trolley and there's zero friction that's acting on the trolley. Once she lets go of the trolley, right, the trolley will actually continuously move by itself without needing you to exert any more force onto it. So interestingly, both of them are actually correct, and this is actually where we derive our idea of Newton's first law. So in the Newton's first law, right, what we understand is that an object that's in motion will continue to be in motion, whereas an object that's at rest will continue to be at rest, unless there's a force that's being acted on them. Alright, so in Newton's first law, we learned that an object in motion will continue to remain in motion if there's no force that's being exerted on it. An object at rest will continue to remain at rest if there's no force that's being exerted. So if you take a look at Sarah's statement, right, is actually possibly true because she actually mentioned that it's not always true about Lisa's statement. So it's possible for an object to continue to move if there's no opposing force that's acting on it. So when could this scenario be possible? Think about it in a vacuum, in space, right? Satellites are able to move around and orbit around the Earth, but there's no need for a propelling force to push it. There's no need for the jet engines to push it anymore in order to move around the entire Earth's orbit, because in space there's vacuum, there's no air resistance. And this actually helps to answer part D also, right? Satellites orbit around the Earth without slowing down and without an engine to keep them moving. Why is that possible? This is because there's no frictional force, or in other words, there's no air resistance that's acting on the satellite, so it will not slow it down at all. So that's where Newton's first law is very obvious, whereby an object in motion will continue to move in motion if no force is being exerted onto it, right? So there's no need for it to exert any more force because there's no air resistance, it will continuously move. Right? I think that this might be the most confusing question in the entire set of work. So if you have anything that you're not sure about, please type it into the private comment. For part 4, we're talking about this concept called lever. Now, lever might be something you've learned in primary school already. So I just want to highlight that a lever actually exhibits the turning effect of a force. So force can be used to turn an object, right? And in this case, a wheelbarrow is being used as an example. And how is the force exerted? It's exerted when the person actually lifts up the wheelbarrow, because the wheel actually acts as what we call the fulcrum, which is the turning point, also known as the pivoting point, right? So we'll talk more about this thing in upper sec. If you have to take physics, we'll learn about moment. Now in 14.2. So for 14.2, we're actually talking about this concept of speed. Now in this concept of speed, it's important to take note of the formula of speed is equivalent to distance divided by time, right? So I think this is not something that's new to us, but of course, do take note that when you're calculating speed, it's important to make sure that you avoid any form of careless mistakes by looking out for what is the unit that's being asked over here. So in this question, we're talking about two sets of runners, if I'm not wrong. Okay, so without calculating speed, we're supposed to find out who is faster, Bode or Griffith Joyner. So in this case, because Bode took a shorter time, so the key over here is to look at time, because the question says without calculating speed. So we're not going to calculate distance over time for both of them. Now, in terms of calculating speed, we are supposed to leave our answers in 3SF now. Okay, so calculation of speed, take note that is equivalent to distance over time. And in this 100-meter race, because I already mentioned that it's a 100-meter race, right? We know that the distance is represented by meters. Now, the time factor over here, as represented over here, Usain Bolt takes 9.58 seconds, whereas the women record was 10.49 seconds. So we can calculate them based on the individual formula of Usain Bolt will be 100 divided by 9.58, whereas the one for Griffith Joyner will be 100 divided by 10.49, and that's how you can calculate the speed. Take note that in your answer, you must write out the unit, okay? Because it's meters per second. Moving on to part 2, right? Speed of an F-16 jet. Now the F-16 jet in this question, they actually mentioned that the speed is about 2,500 kilometers per hour, and they are trying to find out how long will it take to cross the entire Singapore, which is 25 km in terms of its distance. So speed is equivalent to distance over time, as represented over here. Since we know that speed is 2,500 and distance is 25 kilometers, we can sub in the value, and by dividing it by time, right, we can find out that time is actually equivalent to 25 kilometers divided by 2,500 kilometers per hour. This will actually allow us to get the answer of 0.01 hour, right? Because we are looking at a unit of kilometers per hour. But of course, it's important to take note that it is not really that practical to use a unit such as 0.01 hour, because it's not very conventional. So what we can do is we can convert into seconds. How do we convert into seconds? We know that 1 hour is 60 minutes, and every 1 minute is actually 60 seconds, right? So this means that every 1 hour is 60 times 60, which is 3,600 seconds. That's how we can do the conversion here to convert the hours into seconds by multiplying by 3,600. And the answer over here should be 36 seconds. In the next question about the land speed record, right? In the question they asked about this land speed, I think a vehicle, right, called Trust SSC, as represented over here, is actually moving between 2 points that's 1 kilometers apart. Then the time was recorded. So how did it move? So basically, we are supposed to convert certain time units, right? So we are given this timing of 2.96 seconds, and we're supposed to convert it to hours. As I mentioned, 1 hour is 60 minutes, and every 1 minute is 60 seconds. So 1 hour is actually equivalent to 3,600 seconds. Right? So if you want to convert from seconds to hour, you actually have to divide it by 3,600, which is what the question is doing, or rather what the answer is doing over here. Taking 2.96 divided by 3,600, and you end up with this set of value. Right? Take note that you're supposed to leave your value as 3SF, so make sure that it has 3 of the significant figure over here. Next, you're supposed to calculate the speed. Now, in the first part of the question, they actually mentioned that the distance that was being traveled is 1 kilometers apart. So we have a distance factor, and we also have a time factor. That will allow us to calculate the speed by taking distance divided by time, and it should give us this value of 1,220 kilometers per hour. The last question over here, it was actually mentioned that the second round was now 1225.77 kilometers per hour. Just now it was 1220 kilometers per hour, whereas the speed of sound is about 1,200 kilometers per hour. So the question is actually only asking whether this vehicle is moving faster than the speed of sound. And definitely it is, because 1,225.77 or 1,220, both of them are actually greater than this speed of sound as indicated in the question. So definitely it's a lot faster than the speed of sound. Alright, and let's move on to the last page, on page 66, where we are talking about friction. Now the concept of friction over here is something that we have talked about in class quite a lot, about what can be used to reduce them and what could be some of the things that is generated through friction. Just want to point out one of the typo in the workbook, right? You cannot produce heat because based on our understanding of energy, energy can neither be created nor destroyed. So we don't use the word produced heat, right? But the process can release heat, right? So that's what one of the issues with friction, right? It generates a lot of, it releases a lot of heat, and of course it can result in wear and tear, slows down an object, etc. So based on the keywords, it shouldn't be that hard to bring in some of the concept. In terms of uses of friction, over here there's 2 key points before we end off the video. So most fishes have a streamline shape, right? And the purpose of streamline shape in terms of friction, right, is really to reduce the contact area, right? By reducing the contact area, it actually helps to reduce the friction. Right? So the friction gets less between the fish and the water, so that the fish can move faster. So it's important to bring across certain key concepts and their contact area, as well as reducing friction. Why is it hard to run on ice for part B? Because of the smooth surface, right? The smoother the surface, the lesser the friction, and therefore it will make it more slippery. And with that, we have come to the end of this first video. Alright, I hope you have been able to self-mark your assessment. As mentioned at the start, if you have any questions, please post them under the private comment, and I will respond to you accordingly. Thank you.